Okay, so let me talk to you about the topic on bond enthalpy. This is also known as probably the bond energy. And so what this really means is this is a bond energy, bond enthalpy. And this means that this is a bond enthalpy means energy needed to break the bond. Right? I hope this one makes sense to you. So you need 350 kilojoules per mole to break these carbon-carbon bonds. Okay? You have a carbon-hydrogen bond, 410 kilojoule per mole is needed to break that bond. But also what that means is energy released upon forming the bond, right? So once you form the atomic state to form the bond, this is a magnitude of the energy that is shown up. So, but the key point, the main difference is this will be you're going to say, this is about the magnitude. In real term, this is a negative term that is going to be negative energy because energy is essentially going to a lower energy state upon forming the bonding. So the delta H will be a negative value for this concept, for this process anyway. Okay, so but we are talking about the bond energy as a magnitude for this kind of a process. Okay, and what's my second one here is, let's have a look at this reaction. So this is they want to estimate delta H reaction based on this methane, carbon tetrachloride forming chloroform and the methyl chloride in here. So what you need to understand now is this is a delta H reaction, and let me write this equation with showing all the bonds there. So this is a methane. This is a carbon tetrachloride. Okay? And then they want to show how CH with chlorine with a CH3 with the chlorine there. Okay? So that's how this reaction is about. So they want to know delta H reaction on this. And then now why we're talking about bond energy is we are going to talk about the hypothetical state. Okay? And then break these stages into two. One is a delta H1 of 1, which is a breaking bonds. Okay, so then you'll have a carbon with 4 valence. So you're going to break everything, right? Hydrogen with atoms and chlorine with like this. So we are talking about breaking this bond. 1, 2, 3, 4. So we are going to break C. There are 4 bonding that's to be break, and 1, 2, 3, 4. So this is a 4 times CCl bonds. Okay, so those are the bonds. But by breaking all this bond, you are generating this bunch of atoms in a gas state. Then these are atoms, and then finally, what they go is a delta H2, which is a bond formation, which is the reverse of the bond energy process that you see here. So this is not real. This is a hypothetical state. But what I'm trying to say is delta H here reaction is delta H1 plus delta H2 process, right? We are using the fact that this is the state function, so we are just developing one of the possible route, although it's not practically real, but this is one of the hypothetical process, but we have all the information. And then this is the one that saying that, okay, this is on the energy needed, so there will be energy will elevate it. So this is the one. The energy goes up, right, from this methane and carbon tetrachloride state to the higher energies of atomic. So energy level goes up, and then the one from bond formation, the energy level goes down. So this is one, and we are forming this different number of bonds. So let me show you the blue. So this is a bond that need to be formed. This is a bond needs to be formed, right? So this is like 4 times carbon, 3 times carbon tetrachloride with 1 times CH. And then this is a 3 times CH. And this is a 1 times C times Cl. Okay, so what do I do here now is now if you're looking at the answer key, this is what answer key is written. Delta H reaction is delta H of bonds broken minus delta H of bonds formed. They just say that this is an equation that you have to use. But what I'm trying to say here is a much more correct way of understanding this is you just add it up to different enthalpy. This is a reverse of the concept of the bond energy needed to break. So that's why you need a negative sign on there. But this is up to you that which way you want to do. Okay. So then what do I do now is here 4 times delta CH formation, right? Delta H for CH, delta H CH. And 4 times delta H CCl, okay, minus 3 times CCl plus 1 times delta H CH plus, actually I forgot about the delta H's, so let me get that. And then the 1 times delta H CCl, and then the 3 times delta H CH. Okay, so this is a bond formation, but it's a reverse, so I have put in a negative sign, and I want to add it up with something that moving forward by breaking the bond. This is upon forming the bond, which is a negative sign. We're just adding these two processes together. This is how I understand it, but the textbook also wanted to say, bond broken using that number minus bond formed, you can use that number. It's the same kind of concept, but whichever way is your turn. But now, actually, I don't really need to look at the numbers, because if you look at that, this is a 3 and a 1, there's a 4. So it's actually, they cancel out like this. And then if you look at that CH, 1, 2, 3, this all cancel out like this. So at the end, delta H reaction now is 0. Okay, so there is no delta H expected to happen by switching essentially, if you look at that, for example, here, carbon tetrachloride. This thing is all preserved except for they are changing the one of the bond to be like this, right? And this one was like this, and we are just preserving everything and just changing one of the bond to be chlorine. So you just exchange the bond to this and that, but overall the process itself will have no change in the net bond characters. You just have the same number of carbon hydrogen bond and carbon chlorine bond. So therefore your delta H reaction is going to be 0 Kelvin. So delta H reaction for this is 0 Kelvin. And that's more like a prediction based on the simple idea using the bond energy. Practically, I'm sure that this answer is not 0, but it should be close to 0 in real experiment.